there we go. All right, so this is going to be our third example here of an optimization problem. Pretty straightforward. It's going to have some adjacent rectangular corrals, okay, which this is a pretty common thing here. So a rancher has 200 feet of fencing, okay, so 200 feet of fencing. All right, that's referring to our perimeter. All right, and it's going to enclose 2 adjacent rectangle corrals. Okay, so that's important. What dimensions will produce the maximum enclosed area? Okay, so maximum, this is definitely going to be a maximum problem. All right, when I do the optimization problems and I write them out, I'm going to be pretty clear as to whether you're minimizing or maximizing. Okay, so let's take first and draw our picture. All right, I need 2 adjacent rectangular corrals. Okay, so basically 2 rectangles. I'm going to draw one great big rectangle, and then I'm just going to put a line down the middle. All right, this is what adjacent rectangles would look like. Okay, obviously not drawn to scale again. All right, now there's lots of different ways that you could label these dimensions. Okay, but now stop and think about this. If I need 2 separate corrals, and I've got 200 feet of fencing, I've got to have fence all the way around the outside, but I also have to have some fence right here, you know, because cows on one side, maybe, you know, and I don't know, horses on the other, whatever. Okay, so I've got to be able to separate this. Now, when I set this up, I prefer to let my up and down ones be Y. So I've got a Y here, a Y here, and a Y here. Okay, choice is up to you. I just set my Y's there. All right, and then for perimeter around the outside, I want this entire dimension to be X. Okay, and then I set this entire dimension up to be X. Okay, so just trying to get some labels on our little dimensions here, that sort of thing. All right, so what did they give us? Let's write our given down. All right, they gave us the perimeter. And it was 200. Okay, so now I got to come up with my equation. All right, this distance and this distance, I've got 2x. So 2x. I've got this distance plus this distance plus this distance. I've got 3y's. So plus 3y, and it has to equal that 200 feet of fencing. Okay, so being able to set this picture up right is going to determine whether or not you've got this equation right. Okay, now what do I want to do? Well, I want to maximize, and I'm maximizing my area. Okay, now area of the entire thing. So all of this on the inside, I'm maximizing that entire area. Well, area is just length times width. All right, so hopefully you see now why I wanted this whole distance to be X. I don't want to label this and this separate, because when I do my area, I want to just be able to say area is X times Y. Okay, so area equals X times Y. All right, lots of different ways to do this. Okay, but I just find that this pretty much is the most straightforward way to do this. Okay, now we've got our 6 steps. Okay, so our step 1 was solve given for y. Okay, we're going to solve our given for y. So I'm going to take that given equation that I wrote. I'm going to have a 2x plus a 3y equals a 200. Okay, I'm going to go ahead and solve for y. So subtract 2x from both sides. 3y is equal to 200 minus 2x. Now I'm going to divide both sides by that 3. Y equals 200 minus 2x all over 3. Okay. Now, second step, after you've solved for y, plug it into your want. Okay, so plug into want. All right, now I am going to take that want equation. I'm going to write it in terms of the x and y, just like I did there, just a nice little formula. All right. When I plug this in, what I'm doing is I'm creating that function notation. So now I want to turn this into function notation. I want it to be all in terms of x. So that a is going to become a of x. I'm introducing that function notation. All right, this x is going to stay put. I'm going to replace my y with the 200 minus 2x all over 3. Okay, I'm in terms of x now. I really do have a function right here. All right, now I'm just going to go through and simplify this. I'm going to go ahead and distribute that x. I'm going to do this in multiple steps here. So we'll have a 200x minus 2x squared all over 3. And then again, knowing where we need to go with this, we need our derivative. We need our critical points. This is not going to be nice. So I'm going to split this just like, oops, sorry. I'm going to split this just like I did yesterday. A of x equals, let's make this a coefficient in front, 200 over 3x minus that 2/3 x squared. All right, set this up as nice as you possibly can so that you're going to be able to take that derivative kind of easy. Okay. All right, I'm going to go to our third step then. Our third step is going to be to calculate our first derivative and find our critical points. Okay, I'm going to rewrite that function that I just had on the other piece of paper. So a of x is equal to 200 over 3x minus 2/3 x squared. I want to make sure I copy that down right. Okay, so we'll calculate our derivative here. Straightforward polynomial curve here. That 200 over 3x is just going to go to 200 over 3. All right, pulling down power rule right there is going to give me a minus 4/3 and then an x to that first power subtracting 1. Okay, at this point, after I've got that first derivative, we're going to set it equal to 0 so that we can find those critical points. So 200 over 3 minus 4/3 x equals 0. All right, I think I'm going to move the 4/3 over to make it positive. Just going to make the math a little bit easier there. All right, and then again, if you remember, this is arithmetic. You guys can handle this, but multiplying by that reciprocal right there just crosses that out really, really easy, makes it kind of fast. Okay, and again, those 3's then are going to cross out really nice right there. Okay, 200 divided by 4 is going to give me a nice little 50 there. Okay, so on this one, I only got one dimension. Okay, now technically, all right, I do have to verify, but at this point, I should know that that would be my answer, okay, as long as it verifies with our second derivative. Okay, so number 4 here, we're going to take, what was step 4? Step 5, verify. Okay, so we're going to verify with our second derivative. Okay, so I'm going to go ahead and write the first derivative down again. So 200 over 3 minus 4/3 x. Okay, that just gives me something nice to look at right there. Okay, now going to our second derivative. Okay, so that 200 over 3 there, that's going to go away. All right, now this, all right, what's it going to end up being? Just a negative 4/3. Okay, just a negative 4/3. Now, what am I supposed to do at this point? What I'm supposed to do at this point is I'm supposed to plug this in. All right, so my second derivative at 50, but my second derivative is negative 4/3. All right, this is where some people kind of get a little bit lost. All right, now, if you really are very concrete still in your learning and you like to plug something in, like this notation says, I take 50 and I plug it into my second derivative. All right, well, I need a variable to do that. All right, isn't there technically an imaginary x to the 0 power right there? Anything raised to the 0 power is 1. So if you want that concrete, way to look at this, I can take 50, plug it in here. 50 to the 0 power is 1. 1 times negative 4/3 is just going to be negative 4/3. So in other words, this second derivative, no matter what I plug in, is always going to be negative. Okay, because it was a negative 2/3 or negative 4/3, it was constant. Okay, so some of you, just depending on your thinking and how you process, will think of that differently. But having a negative constant there means that second derivative is always going to be negative. All right, so therefore I can conclude that x equals 50 is a max, and that's what we were wanting to do. We were wanting to come up with a maximum value. All right, our step 5 then would be to find our dimensions, whatever's remaining in our problem. Okay, so again, I think I'm going to take that given statement, which was a 2x plus a 3y equals 200, I believe. All right, we got 50 for x. So 50 in here, 50 times 2 is going to be 100 right there. So this is going to be 3y equals 100. And then, of course, that doesn't come out nice. 100 over 3. All right, I'm not going to worry about going to the decimal. I'm going to leave it right like that. There's no reason to switch that out. Okay, assuming I didn't make a mistake. All right, once you get to that point, okay, then you're writing that therefore statement. So therefore, let's see, what was the original problem in? It was in feet because it was 200 feet. So 50 feet by 100 over 3 feet, all right, will maximize the enclosed area. It's the easiest way to put that. All right, so again, this is pretty straightforward with what we did yesterday. The main reason why I wanted to do this example was two reasons, because it was two adjacent rectangular corrals, all right, and then because of the way this second derivative came up, all right, with just being a constant there, I just kind of wanted to make a note of that because that is going to happen a lot, okay? So like I said, how you think about that and how you process that is going to be your choice, but now you've actually seen it. So if it shows up in your homework, then hopefully it'll be kind of straightforward. All right, so was that one straightforward enough? Are we good? Can we go on to the next one, which will be a tad bit more challenging? Anybody have questions over that? Okay, I'm getting silent, so I think that means we're good. All right. Okay. I'm going to give you a minute to copy this down. All right, this one's obviously a little bit shorter. All right, so this will be our fourth example here. It says, find the points on the parabola y equals 4 minus x squared that are the closest distance to the point 0, 2. Okay. Now, at no point on there, I mean, this is worded way differently than what they have been. I'm not asking you to the words maximum or minimum is not in here. All right, but it is kind of implied. Closest distance. All right, closest distance we would be minimizing, right? All right, now, hopefully by now you've got this all drawn out. Okay, so I'm gonna draw this picture. I'm gonna be kind of detailed because I just want to talk about this for a little bit and what the problem is really asking you. All right, this right here. Well, number one, you notice it's already been solved for y. Okay, so like we're not even gonna have that first step of solve our given for y because it's already been done for us. So we're gonna skip that right away. But just in general, what is this? We have this stuff memorized. We know this is an upside down parabola. We know it's been shifted up 4. And with our shortcut method, we can graph it pretty accurately. All right, I don't know that it necessarily needs to be really accurate. Okay, but we know it's shifted up 4. I am kind of making, trying to make a relatively nice drawing here. Okay, let's go ahead and do our shortcut method, our 1, 3, 5 method. So to the right 1, down 1, left 1, down 1. We could go again to the right 1, down 3, 1, 2, 3. It's going to put me right there on that axis right there. Okay, down 3. Okay, so that's pretty accurate there. Okay, not that I'm tracing these very good because that's just the saddest parabola around, but we get the idea. Okay, now I want the closest distance to 0, 2. Okay, so let's put 0, 2 on there. 0, 2 is this point right here. Okay, that is my point 0, 2. All right, now, obviously there's lots of points, multiple points around this very sad looking parabola right here, right? And clearly if I picked a point down here, that distance is pretty far away. All right, but if I picked this one over here, that's closer. All right, I want the closest distance. All right, now if I put, since this is symmetrical around the y-axis, if I pick this point, isn't there going to be another point over here that's going to be the exact same distance? Okay, same thing. If I pick this point, the point that's reflected on the other side is going to be the exact same distance. All right, so I'm just randomly looking at points here. All right, I'm trying to find, or the goal of this, what they're asking you is they want, and notice it is plural. All right, find the points on the parabola that are closest. All right, and because it's symmetrical, we are going to have 2. Okay, all right, so that's just kind of just in general setup for what we got going here. All right, so let's go ahead and do our given and our want and all that kind of stuff. All right, so what were we given? We were given that equation already solved for y. So it takes our first step. We don't have to do that anymore. Okay, now we want to minimize. But what are we minimizing? We are minimizing the distance between our point 0, 2 and what? Some other random point on the circle. which I don't really know what that point is, but any of these, couldn't I let it generically be xy? All right, that's, start the origin, I go over x, some number, I go up y, so then there's my xy point. Okay, so this part, believe it or not, is extremely important for this. All right, I'm trying to minimize the distance to that point, but if we go back to thinking of our distance formula, what do you need? You need 2 points, right? So we know the 0, 2 point, and the point on the circle, we don't know that yet. Okay, now, can I come up with the distance formula and come up with the formula we need? And I can. Okay, so distance is, do we have this memorized? It's the square root. All right, the difference of my x terms. All right, so x minus 0 quantity squared plus the difference of my y coordinates. So y minus 2 quantity squared. All right, so this one, I did really have to refer back to that distance formula. Okay, whereas before, we've kind of been able to just look at our picture and generate our equation of whatever we want based on what it is. Okay, so that's why this one's a little bit more thinking, a little bit more heavy on that. All right, so far so good. Questions? Okay, all right, now, like I said, step 1 is always solve your given for y, but my given is already solved for y. So technically, I'm going to skip that. I'm still going to call step 1, even though it's not our official step 1. All right, so let's go ahead and go to then technically our second step. Well, I put a 2 there. I don't want a 2. First step, I'm going to plug into the 1. Plug into our want. Okay. All right. Now, first of all, I am going to rewrite just so we see it. That y equals 4 minus x squared. Okay. Now I'm going to plug that into my want. All right. Well, what was my want? My want was, again, in terms of x and y initially, so just a plain d is equal to the square root of the x minus 0. I'm going to leave as just x squared. Okay. And then plus y minus 2 quantity squared. Okay. Writing it like that. It is not in function notation. I have x's and y's mixed up in there. Now, when I go to the next line, I am going to turn it into function notation. So d of x. All right. I'm going to replace y right there with what it equals. So I'm still going to have my x squared. I'm going to replace y. So I'm going to have 4 minus x squared minus the 2 that's already there, quantity squared. Okay, so now do you see where this algebra is just going to kind of, like we're going to have a lot of algebra to do underneath here. Okay, I can combine some like terms. Let's clean this up so we have a nice little binomial here. So I'm going to have d of x is equal to x squared plus 4 minus that 2 right there is going to give me a 2. I'm going to go ahead and leave it in front because the x squared is negative. All right, that's not normally how we write binomials, but with that being a negative in front of that x squared term, I definitely want to write it like this. Okay, now again, tons of algebra. This right here, I just need to FOIL out. I need to get this as simple as I possibly can, because where am I going in my next step? My next step is to take the first derivative. So I need this as simple as I possibly can before I take that derivative. Okay, so more algebra, d of x is equal to, all right, so x squared. All right, so FOIL this out. Don't let me make a mistake here. 2 squared and be 4. All right, then a negative 2x and a negative 2x will be a minus 4x squared. Negative x squared times negative x squared will be a positive x to the 4th. Okay, keeping that square root at all times there. All right, now I'm going to put these two together because they're like terms. I'm going to decide to put this in decreasing order, polynomial standard form. Okay, so d of x is equal to, I want that x to the 4th first. All right, putting those two together, I'm going to have a minus 3x squared. Then I'll have the plus 4 with the radical. Okay, now again, all right, you can do it here, you can do it in the next step, whatever. All right, this is obviously when I take this derivative, I'm going to have chain rule. All right, so I would think of this as to the 1/2 power. Not that you necessarily have to show that, but I'm going to be thinking when I take this derivative, it's going to be easier if I raise that to the 1/2 power, then I've just got power rule right there. All right, so Next step, we are to finally some calculus here. We're going to be doing our first derivative and our critical points. Okay, so I am going to rewrite. So I'll have d of x is equal to that x to the fourth minus 3x squared plus 4 to the 1/2 power. Okay, so let's take derivative here of d prime of x. All right, I'm going to pull the 1/2 down in front. Chain rule means what? I leave the inside function alone. So x to the fourth minus the 3x squared plus the 4 stays put. All right, when I subtract 1 from that exponent, I get a negative 1/2. All right, and then hopefully we don't have to do the ddx notation. I can just automatically take that derivative of that inside function, which is going to be a 4x to the third minus a 6x there. Okay, if you still need that ddx notation, feel free to do it. Okay. Let's go ahead and clean this up a little bit. So let's do this. This obviously is going to the bottom because negative exponent. This is going to be in the top. All right, but now when I put this in the top, let's just save some work here. Let's think a little bit. I got a 2 down here in the bottom. Look right here. Do I have a greatest common factor of 2? So when I put this in my numerator, can I go ahead and factor out a 2 at the same time? Okay, so d prime of x. All right, in that numerator, I'm going to take out a 2. All right, that'll leave me with a 2x to the third minus a 3x. Okay, watch my math. Don't let me do a mistake here. All right, this 2 is still in the bottom. This goes to the bottom. All right, I'm going to go ahead and write it as a square root because when we solve it, it'll be easier that way. X to the fourth minus 3x squared plus 4. Okay, so far so good. All right, and then what that allows me to do is just cross off those 2's. All right, just simplified form is going to make it a little bit easier there. Okay, now to find our critical points, what do we do when we have a quotient? We take that numerator, we set it equal to 0. We take the denominator, we set it equal to 0. So 2x to the third minus 3x equals 0. Okay, so let's see. Factor out an x, right? 2x squared minus 3. This turned out okay. X equals 0. Not too bad. All right, this one, let's see. Can we do this in our head? Let's see. 3 on the other side, 3/2. Not going to be a nice number. So plus or minus the square root of 3/2. All right, I'm not going to worry about the fact that that's not nice. Right now, I'm not going to try to go to a decimal. I'm not going to do anything like that. All right, now this one. Let's take square root of x to the fourth minus 3x squared plus 4. Set that equal to 0. All right, so if I square both sides, I can get rid of the radical, right? So then I've got an x to the fourth minus a 3x squared plus a 4 equals 0. Okay, I got to factor this. Okay, now we tried u substitution last year. All right, so or some of you didn't have to do the u substitution because when it was of this form, all right, this is in quadratic form because this was an x to the fourth and this is an x squared. So some of you could just guess and check and trial and error this as being an x squared and an x squared, and then you played around with your factors. All right, this doesn't factor. Okay, this doesn't factor. I've got 4, right? So I can't, 2 and 2 is not going to give me a 3. If I have a 4 and a 1, I got to get a positive 4. I'd have to have a negative 3, so it doesn't factor. Okay, so the only other way then to solve this would be to do quadratic formula. All right, so to save time for this, all right, if you were doing this on your own as a homework problem, you would actually have to do quadratic formula. I can show you a little bit here. It's going to be 3 plus or minus the square root of 9 minus 16 all over a 2. All right, well then, if you know that if I give you that as quadratic formula, well, what's happening right here? All right, you got a negative under that square root, so then we know that these are imaginary numbers. Okay, so I don't have to worry about anything right there. I'm not going to have anything there. So basically, what we have got here for our critical points are these 2 numbers right here. Okay, so right there, there's our critical points. All right, now, normally at this point, okay, we say these are our answers, okay, generally what we do. But what do? We check in second derivative. And so far, every problem we have done, I have said, go to that second derivative and verify with the second derivative, okay? But let's come back up here for a minute. And let's look at this first derivative. Okay, look at that first derivative. Now, polynomial in the top, I've got a radical on the bottom. It's going to have chain rule right there. All right, and it's a rational function, so it's going to be, if I do second derivative, that'd be quotient rule with a chain involved. All right, that's tons of work. The reason we have been doing second derivative to verify up to this point is because the second derivative was really nice and easy to calculate. All right, it will be your choice. If that second derivative is way too challenging, okay, well, revert back to your first derivative test, do a number line, all right, and it's going to be a whole lot easier. It may take a little bit longer, but if you try to do a second derivative and then calculate it wrong, all right, then you know you're not going to be anywhere here. Okay. Okay, so let's do our verify this time with our first derivative. Okay, so what was that first derivative test? Well, what do? We drew a number line, and then we put our critical points on the number line. All right, so basically with having plus or minus the square root of 3 over 2, one's positive, one's negative, they're going to be on both sides of 0. So I know 0 is going to be in the middle. I know my positive 3 over 2, square root of 3 over 2 is going to be there. My negative one's going to be here. All right, so again, it's not crucial that I know what those decimal values are for that. All right, then what do? We do our first derivative, and we have a place for our function here, okay, and we label our intervals. This part takes longer than anything else. 0, square root of 3 over 2, square root of 3 over 2 over infinity. All right, that's just labeling those intervals on there. Okay, I just did that really fast. Okay, so in that first derivative, I think I need to pull it back up here so that we're looking at it, that I'm looking at it and I can see it here. Okay, so we're going to be plugging in a really big negative number. Okay, so this is going to stay negative minus a positive, so it'll have a negative here. All right. That'll be positive. This will be positive. Square root of that, it's going to be positive. So negative divided by positive is going to be a negative. All right, don't let me screw up here. Okay, I'm doing this like really quick off the rough of my head. All right, now we're going to plug in, let's say, a negative 1 from this interval. Okay, so this will be a negative 2 plus a 3. So this is going to be positive. All right, if I do a negative 1 here, I'll have positive, positive, taking square root, I'm going to have positive divided by positive. All right, so this is going to be positive. All right. Plugging in a 1, if I plug in a 1 here, basically I've got 2 minus 3. I'm going to have a negative on top. Plugging in 1 here, okay, I'll have a positive down here on the bottom. So again, this one's going to be minus. All right, plugging in a really big number here, really big number here is going to give me a positive. I'm going to get a positive here. Positive divided by positive should be overall positive right there. Okay, all right, are y'all awake and checking me to make sure I didn't screw up? I don't think I did. Okay, so then that means my original function then would be decreasing on this interval, increasing on this interval, decreasing on this interval, all right, and increasing on this interval. Okay, so we're minimizing this problem, right? We're minimizing. So for a minimum, I need to go from decreasing to increasing. My first derivative needs to go from negative to positive. So then right here would be a minimum. And decreasing to increasing again over here, this would be a minimum. Okay, right here, that's going to be a maximum. I'm trying to minimize this problem, so I don't need that one. So this actually was a really good example. Let's come back here. All right, remember we had said that when we get to our critical points that these are our answers, right? Well, they are, but look at what I've got. I had 2 answers here plus an extra over 0 here. What this turned out to be, these turned out to be the minimum values. This turned out to be the maximum value. Okay, so since the question is asking for minimum, I've got to throw out one of those critical points. Okay, so for a therefore statement, or that would be my last step here. So let's write it, since they're both the exact same point, it's going to be plus or minus the square root of 3 over 2. All right. Ooh. And then we're going to have to plug that into the original function. All right, our original function. All right, that's going to be 3 halves, 4 minus 3 halves, 5 halves. Okay, so the point plus or minus square root of 3 halves, 5 halves, all right, will be the closest to that point 0, 2. Okay. All right, so that one was kind of intense. All right. Process was the same. All the steps was the same. Okay.